Hello everyone. In this lecture I shall discuss the method of variation of parameter to solve a second order non-homogeneous ordinary differential equation. Consider a second order linear non-homogeneous differential equation of the form y double dash plus pxy dash plus qxy is equal to rx. So here rx is not equal to 0 because it is non-homogeneous, and let it be my equation 1. So usually this px, qx, rx are the continuous functions on some open interval I. Okay, this continuity is required because subsequently we want to integrate it. Now as the equation 1 is non-homogeneous, so its general solutions involves the homogeneous solution as well as the particular solution yh plus yp. So now to find y homogeneous, we consider the Rx is equal to 0, and this is my homogeneous equations, and the solution, since the order of this equation is 2, so two constants are involved, and the solution is y1, yh is c1 y1 plus c2 y2, where c1 c2 are arbitrary constants and y1 y2 are not proportional, okay, linearly independent. Otherwise what will happen? Otherwise they can be added together to give a single term, right? That's why it will violate the general solution that its order is 2. So most important fact here is that y1 and y2 must be linearly independent. What we call it? Linearly independent, Li. Okay. Now coming to yp, particular solutions. As we discussed earlier, we know two methods. One is inverse differential operator technique, other one is method of undetermined coefficient, right? Now these two methods can be applied to some specific form of Rx, not for every form, right? Means in particular if Rx is resemblance with its derivative R dash x, then this method of undetermined coefficient will work. However, for any Rx without having any restriction, okay, you say if Rx is your some trigonometric function like sec x, whose derivative is not resemblance with this cosec x, tan x, cot x, log x, e to the power x, or different types of functions, okay, then, or in particular you say for your Euler-Cauchy equations, so here we have to use the method of variation of parameter, okay. So before we have the details of our discussion, let me to introduce myself. Myself, Professor Susanta Kumar Paikray, currently working as a Professor of Mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to tell the details of the solutions. First, let me to tell that what we mean by the linearly independent. Okay, what we mean by the linearly independent, it is somehow necessary. So linearly independent means y1 and y2 are not proportional. One aspect is if y1 by y2 is not equal to k, constant, okay, then y1 and y2 are Li. This is one aspect. The other aspect is by using the Wronskian, okay. Wronskian. This Wronskian is necessary for your method of variation of parameters. So what is Wronskian? Means, so for Li and Ld, for Li linearly independent and Ld, okay, we have one aspect is y1 by y2 is not equal to constant, then y1 and y2 are Li. If equal to constant, then they are linearly dependent. Other aspect is a Wronskian. We find Wronskian, or I say W of y1, y2, okay. So already I have my y1, I have my y2, so it is y1, y2, and we find the derivative of y1 is y1 dash, derivative of y2 is y2 dash, and this is my Wronskian. If this Wronskian is not equal to 0, okay, is not equal to 0, then it is linearly independent. If it is Wronskian is equal to 0, then we call it is linearly dependent, okay, in that way. come to some example. You say here, for example, suppose you say let y1 is equal to 1, y2 is equal to here e to the power x. Then what happens to your Wronskian? Wronskian is 1 e to the power x. It is derivative of 1 is 0. Derivative of e to the power x is e to the power x. So it is e to the power x which is not equal to 0. So it is linearly independent. Okay, otherwise, alternatively, if we see y1 divided by y2 is e to the power minus x, 1 by e to the power x. So e to the power minus x which is not equal to 0. So it is linearly independent. In that way, if we want to think of some more examples, suppose you say y1 is equal to x mod x and here y2 is equal to x square. The interval is 0 less than x less than here 1 less than equal to 1. So here what will happen? What happens to your y1? So this y1 is here x into x, because 0 less than x less than 1. Okay, it is positive, so it is x square itself. It is equal to x square itself. So here y1 by y2 is x square by x square is equal to 1 is a constant. So therefore it is linearly independent. Okay. So it is a constant, so it is linearly dependent. Again, coming to one more example. Suppose you are given y1 is equal to x mod x and your y2 is equal to x square and the interval is say mod x less than equal to 1. So what does it mean? Minus 1 less than is equal to x less than is equal to 1. So here this y1 will be, okay, here we can split in the negative interval minus 1 less than x less than 0 and positive interval 0 less than x less than 1. So here it is the value of mod x is minus x square and here it is plus x square. But you see y1 by y2 is here minus 1 in the negative interval minus 1 less than x less than 0 and it is plus 1 when 0 less than x less than 1. Now it varies from minus 1 to plus 1 which is not equal to your constant, okay, which is not equal to your constant in the whole interval. So therefore this is linearly independent. Okay, so one aspect is you use Wronskian, and here for the discussion of method of variation of parameter we are going to use this Wronskian. Okay, so now let us see the working rule for method of variation of parameter. Now continuing the discussion for particular solution. For some specific form of Rx we use the earlier techniques of inverse differential operator technique and undetermined coefficient technique. Okay, that means if Rx is resemblance to its derivative, right? And for complicated functions, as I have told, sec x, cosec x, tan x, e to the power x, log x, etc. And even if for Euler-Cauchy non-homogeneous equation type, we use the method of variation of parameters. I write VP variation of parameter. Okay, so this method of variation of parameter is one of the powerful methods in the sense that it is applicable to any second order this method is applicable to any second order linear non-homogeneous ODE. However, for finding the parameters, sometimes it is complicated to integrate. Okay, complicated to integrate. Thus, if the previous method will work, we should prefer. We prefer the previous techniques if applicable. And another caution is that the coefficient of y double dash must be 1. Okay, if anything else we first divide it, right? So this caution is that before use method of variation of parameter, ensure that the coefficient of y double dash under equation 1 is unity, means 1. Okay, now let us discuss the working rule for method of variation of parameter. The working rule follows. Working rule runs as follows. Consider the differential equation y double dash plus pxy dash plus qxy is equal to rx. So step 1, we find the homogeneous solution. Step 1, the complementary function is of the form, the complementary function YH is of the form as I have told you here, it is YH is C1 Y1 plus C2 Y2 as I have discussed here, homogeneous part. Okay, then what is your YP? Step 2. Then what is your Y particular solution? For your Y particular solutions, we have some U into Y1 plus V into Y2. So this C1 is replaced by U and C2 is replaced by V. So V is a function of X and U is also a function of X. So now this U and V are two parameters. Okay. So now we have to find what is U and what is V. So here we can say this U and V, these are all the parameters. Okay, these are the parameters. Right, now the thing is that what is U? Where U is equal to, so I can say where U is equal to integral minus of Y2 into R the Wronskian, R is the right hand side, divided by the Wronskian dx. Okay, Wronskian dx. And what is your V? And your V is equal to integral Y1 into R Wronskian divided by W dx. And what is here Wronskian? I have already told, with Wronskian is Y1 Y2 Y1 derivative Y2 derivative determinant. Okay, so this is the thing. First we find the homogeneous solution, then we replace this constant for the particular solution by the parameter U and V, Okay, and just to recall the formula for U and the formula for V. Okay, so this is your U minus Y2. You see, for U we have a minus sign here, minus Y2 into R by W dx Wronskian dx, and for V it is Y1 into R divided by the Wronskian dx, where the Wronskian is this Y1 Y2 Y1 dash Y2 dash determinant. Okay, so this is the technique, and since the constants are replaced by the parameters U and V, this method is known as the method of variation of parameter. Now in a remark I can write the constants C1 and C2 present in the homogeneous solution being replaced by the parameters U and V. So this method is known as method of variation of parameters. Okay, so let us see some illustrative examples. Use method of VP to solve this. Okay, so coming to the solution, let y double dash plus 4y is equal to tan 2x for complementary function y homogeneous. Let y double dash plus 4y is equal to 0, putting y is equal to e to the power lambda x, the auxiliary equation becomes lambda square plus 4 is equal to 0. So lambda is my plus and minus 2i. It is a case of complex conjugate. Therefore y homogeneous is c1 cos 2x plus c2 sin 2x. You see, so what is your y1? So this is my y1, is not it? And this is my y2, sin 2x is my y2. So next we find the Wronskian. Okay, so where y1 is equal to cos 2x and y2 is equal to sin 2x. Okay, now we have to find Wronskian. Now here Wronskian is equal to y1 y2 y1 dash y2 dash is equal to cos 2x sin 2x. The derivative of cos 2x is minus 2 sin 2x. Derivative of sin 2x is 2 cos 2x. The determinant, if you find this determinant, it is twice cos square 2x plus twice sin square 2x. So this is 2 into 1 is equal to here 2. Okay, sin square theta plus cos square theta is 1. So therefore the Wronskian is equal to here 2. So now we are ready to find the particular solution here. Next the particular solution B. Next the particular integral or yp be given as here y particular is u into y1 plus v into y2, where u is equal to integral minus of y2 into r by Wronskian dx, and v is equal to integral y1 into r by Wronskian dx. So here thus u is equal to here integral of y2 is here sin 2x minus of sin 2x, and r is here tan 2x divided by Wronskian is here 2. So this is equal to minus of 1 by 2. It is sin 2x by cos 2x dx. So this is equal to here minus half integration of this is sin square 2x by cos 2x dx. So I can write it minus half integration of 1 minus cos square 2x divided by cos 2x dx. So this is equal to minus half integration of 1 by cos 2x is sec 2x minus cos square 2x by cos 2x is cos 2x dx. Okay, so now we evaluate the integration of sec 2x is ln sec 2x plus tan 2x. Okay, so because of this 2 we divide this 2 again here, and the integration of cos is sine. Okay, so it is minus this 2 is again divided 1 by 2 sine 2x. Okay, so this 2 is considered here. So this is equal to here minus of 1 by 4. So this will be my minus of 1 by 4 ln sec 2x plus tan 2x minus 1 by 4 sin 2x. So this is my yp. So therefore the general solution is next here v is equal to integral y1 r by Wronskian dx. So what is your y1 is y1 is here cos 2x. So cos 2x integration of cos 2x, r is tan 2x means sin 2x by cos 2x by Wronskian. This Wronskian is here 2. So cos 2x is cancelled. So this is integral half sin 2x. So integration of sin 2x is minus cos 2x by this constant. So this is equal to minus 1 by 4 cos 2x. Okay. So actually this is a minus sign and minus, and it will be a plus. Okay. So now this is minus 1 by 4 cos 2x. So thus here y particular solution is uy1 plus vy2. So this is equal to here u is this is here u. Okay, so this is equal to uy1. So we can write it minus 1 by 4 ln sec 2x plus tan 2x plus 1 by 4 sin 2x, and here y1 is cos 2x plus v is minus 1 by 4 cos 2x into y2 is here sin 2x. Okay, sin 2x. So now hence the complete solution is y is equal to y homogeneous plus y particular. Okay, or you may write it where y homogeneous is this much and y particular is this much. Okay, so this is your answer, because these are all lengthy. Okay, so why should you write? You can write it where this and this, and come to one more example. Next you are asked to solve this. You see the right hand side is cot x. Okay, so the previous operator method and also by the method of undetermined coefficient will not work. So coming to the solution, the solution of homogeneous part is here d square plus 1 into y is equal to 0. the auxiliary equation is lambda square plus 1 is equal to 0. So this implies lambda is plus and minus I. So therefore here y homogeneous is c1 cos x plus c2 sin x. So this is my y1 and this is my y2. Now my Wronskian is y1 y2 y1 dash y2 dash determinant. So this is cos x sin x and this is minus sin x cos x. Determinant is cos square theta plus sin square theta is 1. So therefore your Wronskian is equal to 1. For particular integral yp, let yp is equal to u into y1 plus v into y2 with u is equal to minus y2 into r divided by Wronskian dx. This is equal to minus of sin x into cot x. Cot x is cos x by sin x divided by Wronskian is 1 dx. So this is integral of cos x. So this is simply minus of sin x. Okay. So here u is minus of sin x with this and here v is equal to integral y1r by Wronskian dx. So this is equal to y1 is here cos x. This is cos x by sin x and the Wronskian is 1 dx. So this is equal to cos square x is 1 minus sin square x by sin x dx. Okay. So this is 1 by sin x is integral of cosec x dx minus here sin x. Okay. Sin x dx. So I integrate cosec x. The integration of cosec x is minus ln cosec x minus cot x, and integration of sin x is minus cos x, so it is plus cos x. Thus y particular is equal to uy1 plus vy2. So this is equal to minus of sin x into cos x plus vy2. V is here cos x minus ln cosec x minus cot x into y2 is here sin x. Okay. Consequently the complete solution is y is equal to y homogeneous plus y particular. Okay. So this is equal to here c1 cos x plus c2 sin x plus you write this y particular thing here. Okay. Or you may write it here yh is this and yp is this. In that way you should write. Okay. So this is your answer. Coming to next example. So next, coming to the solution of this. Okay, here y homogeneous is c1 cos x in the similar lines plus c2 sin x, and accordingly here Wronskian is 1 and y particular is uy1 plus vy2. We have to find what is u and v. So here u is equal to minus of y1r by Wronskian dx. So this is equal to, and here Wronskian is 1. So minus of y2 is here. This is here y2. Okay, this is here y2 and this is here y1. Okay, this is here y1. So here minus of y2 is sin x into Wronskian is sec x, means 1 by cos x dx. So this is simply the integration of minus integration of tan x dx is minus ln sec x, or you can write it ln cos x. So here u is equal to ln cos x. Again here v is equal to y1r by Wronskian dx. So this is equal to integration of cos x into sec x dx is simply here integration of dx is simply here x. So therefore here v is equal to x. Thus here yp is equal to uy1 plus vy2. So this is equal to u is here ln sec x means ln cos x. y1 is cos x. Cos x ln cos x plus by2 x sin x. Hence the general solution is y is equal to y homogeneous plus y particular. So I can write it c1 plus log cos x into cos x plus c2 plus x sin x. Okay, sin x. So this is the answer. So most importantly, this v and u, sometimes these are complicated. Okay, this v and u. Once v and u you obtain, then your job is over. So next, solve this. Okay, so here Rx is cos x. So solution as usual, here y homogeneous will be c1 cos x plus c2 sin x. Therefore y1 is here cos x, y2 is here sin x, and accordingly you find here Wronskian is here 1. So therefore y particular is uy1 plus vy2, and importantly here what is here u is equal to minus of y2 r by Wronskian dx. So here y2 is sin x into cosec x dx, means simply integration of dx is equal to x. So here u is equal to here x. Now coming to here v, integral y1 r by Wronskian dx. So here y1 is cos x into cosec x 1 by sin x. So this is equal to here integration of cot x dx. Integration of cot x is log sin x, ln sin x. Okay, so therefore v. So after getting u and v, you find, so therefore you find yp is uy1 plus vy2, and consequently and subsequently, therefore hence the general solution is y is equal to yh plus yp is equal to this. Okay, now coming to certain Euler-Cauchy equations. Now you see this is a Euler-Cauchy equation. Okay, Euler-Cauchy equation. So for Rx we have to divide it. Okay, so now you have your homogeneous solution y double dash x square y double dash minus 2x y dash plus 2y is equal to 0. So putting y is equal to x to the power m, the auxiliary equation is here m square plus a minus m. This is here a minus 2 minus 1 m plus b is equal to 0. So this is the auxiliary equation. So that means here m square minus 3m plus 2 is equal to 0. So that means here am is equal to 1 and 2. Okay, so this implies y homogeneous is c1x plus c2x to the power 2. This is your homogeneous solution. So what is your y1? So this is your y1. So y1 is equal to x. That is my y1 is equal to x and y2 is equal to x square. So this implies my Wronskian is y1 y2 y1 dash y2 dash. So this is equal to x square 1 2x. You find this determinant. It is 2x square minus x square is x square. So this implies my Wronskian is equal to x square. Okay, so now you divide, let it be your equation given equation 1, dividing x square to both sides of 1. Now dividing x square to both sides of 1, we have Rx is equal to x cube cos x divided by x square. So this is equal to x cos x. This is important. Okay, Rx we got. So now next year what is your y particular? Next year y particular is equal to uy1 plus vy2 with what is your u is equal to integral minus of y1r by Wronskian dx. So this is equal to integration of minus of y1 is here x, Wronskian is x cos x divided by here x dx. 1x is cancelled. So integral of minus of x cos x dx. We use by parts of integration. So apply integration by parts. Minus of first integral second minus integral derivative of first into integral of second, it is minus cos x. Okay, so this will be here minus of x sin x minus of cos x, minus plus minus cos x. So this is your u. Okay, this is your u. And what is your v? And v is equal to integral y1r by Wronskian dx. y1, there is a simple mistake in the formula. U is y2r by Wronskian. y2 is x square, and Wronskian is also x square. Wronskian is also x square. Okay, Wronskian is also x square. So x square cancel, x remain there. Okay, now it is same. Now it is your y1r. So your y1 is x, r is x cos x divided by Wronskian is x square dx. So x square cancel. Integration of cos x is simply here sin x. Okay, so therefore here v is equal to here sin x. That means y particular is u y1 plus v y2. So this is equal to minus of x sin x plus cos x into x plus sin x into x square. Hence the general solution y is equal to yh plus yp. So this is equal to c1 minus x sin x minus cos x into x plus c2 plus sin x into x square. So this is equal to, here this is c1x plus c2x square minus x cos x. Okay, so this is your answer, right? So now on the next example 6. So for your homogeneous solution, x square y double dash plus 4xy dash plus 2y is equal to 0. Auxiliary equation is m square plus 4 minus 1m plus 2 is equal to 0, implies m square plus 3m plus 2 is equal to 0. So this implies here m is equal to minus 1 and minus 2. So therefore yh is c1 x to the power minus 1 plus c2 x to the power minus 2. So here what is your y1? y1 is 1 by x, y2 is 1 by x square, and I find the Wronskian. What is rx? One more important thing. What is your rx? rx is equal to sin x divided by x square, is sin x divided by x square. Now what is your Wronskian? So next, what is your Wronskian? Wronskian will be y1 y2 y1 dash y2 dash. If you simplify, it will be here 1 by x fourth. Wronskian is 1 by x fourth. So therefore y particular is equal to u y1 plus v y2. U is equal to minus y2r by Wronskian dx, and y2 is here minus of 1 by x square. Wronskian is sin x by x square divided by 1 by x fourth dx. So this 1 by x fourth, this x square cancelled. Integration of minus sin x is here. So integration of minus sin x is simply cos x. So this is your u. Accordingly, you find what is your v. V is y1r by Wronskian dx. If you simplify it, it is integration of x sin x dx. So if you integrate by parts, x cos x minus sin x. So by parts, integration by parts. So therefore your y particular is this, and general solution is y is equal to yh plus yp, where yh is this and yp is this. Okay, let me to solve one more question. Coming to the last example, here homogeneous solution, here y double dash plus 3y dash plus 2y is equal to 0. Here auxiliary equation, putting y is equal to e to the power lambda x. The auxiliary equation is lambda square plus 3 lambda plus 2 is equal to 0. So lambda is equal to minus 1 minus 2. Y homogeneous is c1 e to the power minus x plus c2 e to the power minus 2x. So let my y1 is e to the power minus x and y2 is e to the power minus 2x. So my Wronskian is Wronskian is y1 y2 y1 dash y2 dash. So if you evaluate it, I will get e to the power minus e to the power minus 3x. Next my y particular is here u into y1 plus v into y2, where my u is equal to integral y2r by Wronskian dx. So this is equal to minus of e to the power minus 2x, and r is e to the power x divided by minus plus, it becomes e to the power minus 3x dx. So this is equal to here this and this, e to the power x into e to the power x dx. If you put e to the power x is equal to some t, then this will be your dt, this will be your dt, is not it? So it will give you integration of e to the power t means e to the power t means e to the power x is my u. So what is my v now? My v is equal to integral of y1r by Wronskian dx. So this is equal to integral e to the power minus x e to the power x by minus e to the power minus 3x dx. Okay, so this is equal to minus of integral of e to the power 2x into e to the power x dx. I can split it, minus of e to the power x into e to the power x into e to the power x dx, is not it? So if I substitute, this is equal to my t, okay, then this will be my dt, and this will be my t, so this is equal to minus integral of t e to the power t dt. It will have this form. Okay, so applying integration by parts, minus of t e to the power t minus 1 into e to the power t. So this is equal to minus of e to the power t taken common, it is t minus 1, putting t is equal to e to the power x minus e to the power x into e to the power x minus 1. Okay, so this is, so therefore your y particular is uy1 plus vy2, accordingly you write, and general solution is u is equal to u homogeneous plus u particular, where u homogeneous is this and u particular is this. Okay, so this is the answer. Just coming to some key aspect, a second order non-homogeneous linear equation is given. Any such equation can be solved by variation of parameter. The only thing, complication may arise during finding u and v. Okay, so if previous method works, then we apply, otherwise we apply this method of variation of parameter, and in particular if it is a Euler-Cauchy equation, then we can proceed by this method of variation of parameter, but the caution is that the coefficient of y double dash should be 1, then only the Rx will be obtained. Okay, this is most important. So now the video is getting lengthy, we should close it here. Now my appeal to all of you at this stage, if you find this lecture is helpful and interesting to you, please like and subscribe to this channel, which will boost my motivation so that I can upload subsequent lectures for your benefits. Okay, so thank you all, have a nice day.